All right, this is the classic ladder leaning against a wall example that you will see in almost every calculus textbook. This example, very similar to this, is in our textbook, but I mean, it's a great example, so I'm going to use it. So the example is you've got a ladder leaning against a wall, and then the base of the ladder starts to like slip away from the wall. So if the ladder's leaning against the wall, the base is going to slip away, and as that happens, the top of the ladder is going to slide down. And the ladder's going to slide all the way down and hit the floor. That's the idea. But what we have here is that the base of the ladder is sliding away from the wall at some constant rate. So that's 2 feet per second. And the question is, how fast is the top of the ladder sliding down the wall when that top is 6 feet from the floor? So we're going to solve this problem using the dreads method. So first, we're going to draw a diagram. We have a wall, and we have a floor, and we have a ladder. And the ladder is leaning against the wall. So I'm going to draw myself a little ladder here. That's my ladder. Now the ladder is 10 feet long. The length of this ladder is a constant. It's not changing over time, okay? So the length of this ladder can be labeled with a constant value in the diagram. So that's going to be 10 feet, okay? Now, there's another constant in here that's easy to forget about, and that is that the wall and the floor form a right angle. So this right here is a 90-degree angle. That is not stated in the problem, but it's assumed. Walls are usually at 90-degree angles with the floor. Okay, so we're going to take that for granted. And then the other relevant pieces of information, like the other relevant values we should label in here, are the distance between the wall and the base of the ladder. I'm going to call that x. And then the distance between the floor and the top of the ladder, I'm going to call that y. So there's my diagram. And I labeled the constants, the known values, and I labeled the unknown values and gave them names using variable letters. So now we're going to identify rates, both known and unknown rates. So the rate that's given to me is the rate at which the base of the ladder is sliding away from the wall, 2 feet per second. So using the variables that I decided to use, that is the rate of change in x. So I'm going to write dx over dt, the rate of change in x with respect to time. It's increasing because the base is sliding away, so x is getting bigger. So this is a positive rate of change of 2 feet per second. There we go. Now, that's the rate I know. What is the rate I want to know? How fast is the top of the ladder sliding down the wall? That's the rate of change in y, right? It's the distance between the top and the floor. So that's dy over dt. I'm going to write that down. I'm going to say that equals what? Okay, I like to put that in my, I like to write that down to remind myself what it is that I'm trying to solve for. So next, I'm going to come up with an equation. And what I want to do is choose some kind of equation that is based on this triangle that involves the variables that I know the rate of and that I want to know the rate of, as well as any constant values that I might happen to know. So in this situation, I have the length of the ladder. I might as well use that since it's a constant. And I've got the x and y variables. Let's find out an equation that involves those three. I bet you already know what it is. We're going to use the Pythagorean Theorem and do x squared plus y squared should equal 10 squared. So that's x squared plus y squared equals 100. Okay. I could have chosen some other equation like a sine or a cosine ratio, but that would have involved angles, and I don't know anything about the angles except for the right angle, and I also don't care about the angles. So because I'm not trying to find the rate of change in the angle. So I'm going to avoid using angles. So my next step is to differentiate. And it's with respect to time. Just a reminder. So I'm going to do the derivative with respect to time of x squared plus y squared, and that'll be the derivative with respect to time of 100. And here what I need to do is differentiate the x squared. But then since x is a function of time, I need to apply the chain rule and multiply by the derivative of x with respect to time. So I got 2x times dx over dt. Same thing with the y. It's 2y times dy over dt. But on the right side, since the hypotenuse squared is a constant, that derivative is 0. I'm going to clean this up a tiny little bit. I'm just going to divide both sides by 2 to simplify this up a little. So I'm going to have x times dx over dt plus y times dy over dt still equals 0. So there's my differentiated version. So I started with an equation, and then I differentiated that equation, and now I have a new equation that involves both variables and rates of change in variables. So the next step is to substitute. This is the moment where we get to plug in the when the top of the ladder is 6 feet from the floor. That part, like that identifies the moment in time that we're interested in examining. So that would be a specific value of the variable y. So we're going to have y equals 6. Now, what I need to do is in this differentiated equation, replace all of the variables with values, except for the one rate of change that I'm trying to solve for. So I'm going to be able to stick in a value for y. I'm also going to be able to stick in a value for dx over dt. We have that. That's 2. I want to solve for dy over dt, but that still leaves x. And so I need to figure out what x is. But luckily I have this equation that relates x and y to each other, and I know y. So what I need to do is solve that, stick that y equals 6 in there and solve for x. So I'm going to have x squared plus 6 squared equals 10 squared. Solve that. We got 36. We got 100. X squared is going to be 64. So x is 8. You don't have to worry about -8 because we're dealing with distances here, lengths, right? So y is 6 feet and x is 8 feet. So those are the two values that I want to substitute into my equation, along with also the dx over dt. So let's put all that in there. Okay, so taking this equation, starting with x. X is 8 feet. 8 feet. Multiplied by dx over dt, which is 2 feet per second. And then plus the y value, which is 6 feet, multiplied by dy over dt, which is my unknown, equals 0. Okay, folks, it's time to solve. I'm going to solve this now. So we've got 8 times 2 is 16. This is feet squared per second, technically. We've got 6 feet per second, or feet times dy over dt equals 0. Let's see, 6 feet times dy over dt is going to be negative 16 feet squared per second. And then we're going to divide both sides by 6 feet. Feet will cancel out. Divide by 6 feet. One of the foot will cancel with one of the feet factors up there. And then we get our answer, which is 16 divided by 6. Negative dy over dt is going to be negative 2.6 repeated feet per second. And we did it. That's how fast the top of the that's how fast the top of the ladder is sliding down the wall when it's 6 feet from the floor.